Hello everybody, welcome to the second half of chapter 4.1, and what we're going to focus on in this video is the finding particular solutions when integrating. And that's really our only objective, as you can see. What I'd like to start off is a conversation about initial conditions and particular solutions. So let's write that out. Initial conditions and particular solutions. Okay. And what I'd like to do here is just kind of bullet point some thoughts so we can kind of make a little bridge to our next concept here. So first of all, I'd like to just kind of state that the constant C means that any number of solutions could exist when finding an antiderivative. We explored a little bit in the last video exactly why this is true. We substituted in about 3 different values for C and we got the same derivative every single time. So that really just goes to show that the kind of blank space C that we can fill in anything with leaves us with any number of solutions that could happen. And so that's why we find an antiderivative, right? Like a general solution. That's what we found yesterday in yesterday's video. So what we want to find this time is a particular solution. And we're going to say to find a particular solution, not a general solution, we need to have an initial condition. Okay, an initial condition. And what an initial condition is, I'm going to underline it again. An initial condition is an ordered pair that the antiderivative passes through. And we can do a quick example of this. So, let's say we had the antiderivative of 3x squared minus 1. And we know from yesterday's power rule what this would end up being is 3 times x to the third over 3 minus x plus c. We simplify this piece to become just x to the third because the 3's cancel each other out. So I get x to the third minus x plus c. That's our general solution. We learned about that yesterday. Now, let's put an initial condition to this. So let's say that we have an initial condition is the point 2, 4. Right? And again, what that is really saying is that the curve passes through 2, 4. And here's what we do with that information. What we're interested in, remember this is like saying big F of x equals this. So we want to find out when F of 2 equals 4. So we substitute in 2 cubed minus 2 plus c, and we know this is going to equal 4. So we're going to have 8 minus 2 plus c equals 4, 6 plus c equals 4, c equals negative 2. Okay, so what I actually have, when I find the c value, I found my particular solution. So I know now that f of x is x cubed minus x minus 2. I fill in that minus 2 for the c value for my general solution, and now I have a particular solution. Okay. Let's try that one more time. So, our example asks us to find the general solution of big F prime of x equals e to the x. And remember, I can find just regular big F of x, pardon me, there we go, if I take the antiderivative of e to the x with respect to x. And what I can do here is understand, this is again a rule of integration that we looked at yesterday in the textbook with all of those rules of integration. The antiderivative of e to the x is just e to the x plus c. And we want to know also I didn't write down, pardon me, okay, so sorry, let's finish writing out this question. This is the general solution, but let's finish writing out the question, because it said find the general solution of f prime of x equals e to the x, and the rest of that question, sorry about this, asks, and the particular solution that satisfies the initial condition that f of 0 equals 3. Okay, so we really have done the first half of this question already. We found the general solution, and now we're going to use this initial condition to find a particular solution. And here's how we can do that. We can evaluate f of 0, so we can say f of x equals this. So f of 0 equals e to the 0 plus c, and we know that this is going to be equal to 3. So when I continue to simplify here, I get 1 plus c equals 3, not c, pardon me. And then I would subtract 1 from both sides, and I'd find that c equals 2. So my particular solution is that big F of x equals e to the x plus 2. And that is my particular solution. Okay, with this initial condition satisfied. All right. Let's talk about vertical motion. Can you see that okay? Yeah, okay, awesome. And the problem we're about to do is a really cool one because it really kind of illuminates for us how antiderivatives are really, really helpful. They help us kind of work backwards. When we're given certain information, we can use these initial conditions to kind of piece together from given certain derivatives, we can work backwards from them. And it's really kind of cool. We can create whole new functions given these antiderivatives. And we'll go over what I mean. But here's our problem. A ball is thrown upward with an initial velocity of 64 feet per second from an initial height of 80 feet. First, we are asked, part A is going to ask us to find the position function giving the height s, little fancy s, as a function of the time t. And part B, we are going to answer, when does the ball hit the ground? Okay. When does the ball hit the ground? let's talk really quickly about what we've done before. Before differentiating, we've been able to answer part B. Typically, we're given a position function, and we're able to answer part B, right, when that derivative is 0. And we're going to get there, but first we have to create this position function in the first place. We don't have one yet, but we can create one using our initial conditions. And here's what we can do. Let's list out what we have initially. We have a few things given to us initially, right? Initial velocity is 64 feet per second. And then we have, I'm going to use a different blue. Let's see if it shows up. Oh yeah, pretty well, okay. The initial height, the initial position is 80 feet. Okay, so here's what that means in function notation. We know that when t equals 0, that's our initial time. So here's how we write those initial conditions in terms of time. We can say that our position, our s function, our s of 0 is equal to 80, right? Because our position at 0, our height at 0 is 80. Our derivative of that, our velocity, so our s prime of 0, is 64, right? Initially, our velocity is 64. And we know one more thing because we live on the planet Earth. We know that our acceleration is the second derivative of your position function, so s double prime. Our acceleration is always going to be negative 32 feet per second per second. It sounds kind of silly, per second, but that's just what it is on Earth always. That's gravity for you. So, again, I'm going to write out in another color here why we know these things. The position when time is 0 is 80. That's because we knew the initial height was 80. We know s prime, our derivative, our velocity, was 64 because the initial velocity was 64. I should say feet, and 64 feet per second. And then 32, we can say that that's just acceleration due to gravity, and that's negative 32 feet per second. Okay, kind of fun stuff there. So what we can do here is we can start with the very bottom. We can start with the second derivative. We can integrate it, and then we'll arrive at an s prime function. And if we integrate this, we'll arrive at a position function, because that's what integrating allows us to do. It allows us to kind of work backwards. So let's start this off. To begin, we should, like I said, use that negative 32 to help us get started. We know we can find s prime of t. We know we can find the velocity function if we integrate our acceleration. So we're going to integrate negative 32 with respect to time, so negative 32 dt. And what that means is we're going to have a velocity function then of negative 32t plus c. And this is a general solution. It's not totally helpful to us yet, but we can find a particular solution if we go back and we look at our initial condition for velocity. We know velocity is, when time is 0 for velocity, we have a velocity of 64. So let's substitute in that 0 here and set it equal to 64. Negative 32 times 0 plus c, we know that has to be 64 because this is s prime of 0. All right. And when we solve that, the 0 piece here would just cancel out, and we get the statement c equals 64. So I can safely say then that s prime of t, my velocity, is negative 32t plus 64. And now I can continue to work backwards. I'm going to take this velocity function and I'm going to use it to find my position function, my s of t. I know I can find that by integrating s prime of t with respect to time, again dt, that's what respect to time looks like. And I know that I can fill in s prime of t with what I just found, so I'm actually integrating negative 32t plus 64 with respect to time. And when I go through all of this, what I get is negative 32 times t squared over 2. This comes from the power rule of integration, plus 64t plus c. And when I simplify, I get negative 16t squared plus 64t plus c, because negative 32 divided by 2 is 16. All right. Again, I've arrived at a general solution for my position function. However, that's not entirely helpful. What I need to do is I need to use my initial condition, which was s of 0, position function at 0, was 80. So I'm going to set that up. S of 0, so negative 16 times 0 squared, plus 64 times 0, plus c equals 80. When I solve this for c, the 0 pieces just cancel out, right? 0 and 0, and I get c equals 80. So now I have found a position function with respect to time, negative 16t squared plus 64t plus 80. Fabulous. Part A is taken care of. This is our position function with respect to time. Now, what I can do to answer part B is set this equal to 0. Remember, when our position is 0, that is when we can find the time that the ball reaches the ground. So I can begin that process by factoring. And let's just write out what we're doing kind of in words first. So the time that the ball hits the ground, time the ball hits the ground is found by setting the position function equal to 0. The time the ball hits the ground is found by setting the position function equal to 0. So let's do just that. Let's say negative 16t squared plus 64t plus 80 equals 0. Again, I gave you guys the first clue. We're going to be factoring this. So what we can do is we can see that they all have a 16. I'm going to take out a negative 16. And when I do that, I left inside, I have t squared minus 4 minus 5. When I factor this, minus 4t. When I factor this quadratic inside, I get negative 16 outside, t minus 5, t plus 1. When I set both of these equal to 0, I get t equals 5, and I get t equals negative 1. Now remember, we're talking about the concept of time. Time cannot be negative, so 5 is the only answer that's plausible within our domain. So we can say then, kind of circle this guy, maybe cross this one out, that the ball hits the ground after 5 seconds. Okay, we're going to start off class tomorrow with another one of those, but that is all I have to show you today. So thanks for watching. We'll see you in class tomorrow.